As for larger numbers, it becomes harder to find the GCD by inspection. So this kind of shows us that the GCD is formed out of the prime numbers at the minimum exponent that it appears between the two integers. So if I have the prime factorization of A and I have the prime factorization of B, they're each going to be formed of prime numbers to a certain exponent. And to find the GCD, you take each of the prime numbers to the lowest exponent between the two. Okay, so let's use that method. So this is again the familiar method that you probably learned in school to find the GCD of two numbers, of two integers. So let's break up. 120 is 12 times 10. 12 is 4 times 3. And 10 is 2 times 5. And then 2 times 2 times 3 times 2 times 5. So they're all primes. We're going to collect them. This is 2 to the 3 and 3 to the 1 and 5 to the 1. And let's do 500. So this is 5 times 100, which is 5 times 10 times 10. 5 times 5 times 2 times 5 times 2. So we get 2 to the 2 and 5 to the 3. Okay, so the GCD of these two numbers. So each factor to the lowest exponent. Okay, so the 2 to the lowest exponent, the 3 to the lowest exponent will be 3 to the 0 because it doesn't appear there. 5 to the lowest exponent is 5 to the 1. So we have 4 times 5, which is 20. So 20 is the GCD of both of these. All right. We can find the lowest common multiple of two integers in a similar way. So lowest common multiple is the smallest positive number that is divisible by both A and B. And the lowest common multiple is all the prime numbers in the prime factorization of A and B taken to the maximum of the exponent. All right, so in example 12, I have two numbers already with their prime factorization. So the LCM of these two numbers, we're going to compare. So 2, the highest power between the two is 4. 3, highest exponent is 5, and 7, high exponent is 2. Okay, so you can leave it like that, or you can expand it out. 2 to the 4, 3 to the 5, 7 to the 2 is 1, 9, 0, 5, 1, 2. So that's the LCM, the smaller number that they both divide into. And there's a theorem that connects the GCD and the LCM. For A and B positive integers, then the product of the two integers is going to be the product of the GCD times the product times and the LCM of the two numbers. So this theorem is sometimes useful in working with integers. Okay, we might see it along the way. All right, so this brings us to the Euclidean algorithm. Okay, so the Euclidean algorithm, again, is sort of the algorithm is written here, but I'm going to explain with examples. So this is a way of finding the GCD of two numbers, of two integers, not by using the prime factorization. The prime factorization is not the most efficient way to find the GCD for large numbers because it involves kind of breaking things into primes, which is sometimes sort of not the most efficient. So this is very similar to the divisibility kind of formula. Basically says that if we're going to take our first integer a and write it as the product of the other integers times the quotient plus the remainder. So we're basically dividing a by b and finding the mod each time. All right. And then the GCD of the original number is equal to the GCD of b with the remainder. So we're going to repeat this process. We're going to take b and r and write it in this fashion and find the remainder. And then basically we're going to do a repeated algorithm until we get to a remainder of the greatest divisor is the last non-zero remainder in the sequence of divisions. Okay, so this is a fairly standard algorithm for finding GCD that's a bit more efficient than with the prime factorization. So this is kind of, up to now, there's been a lot of definitions and theorems, and here's how to kind of do prime factorization. This is probably the first sort of new thing that we're doing in this section, and that's probably good. This is the main method that we learn in this section. All right, so our numbers A and B are 414 and 662. So we're going to take like A to be our larger number and B to be our smaller number. So we're going to divide 662 by 14 and write it as the product plus the remainder. Okay, so 662 divided by 414 is 1. Okay, so 62 is going to be 414 times 1, and then plus the mod, plus the remainder. So 662 minus 414 gives me a remainder of 248. All right, so just kind of to keep with the algorithm above, this is A, and this is the B, and this is the quotient, and this is my remainder. Okay, so what the theorem above says is that the GCD of erase. Okay, the GCD of A and B is going to equal to the GCD of B and R. All right, so we're going to now take our numbers as the B number and the R. So the B and the remainder, and we're going to repeat the process. So 414 divided by 248, it goes in once. All right, so it's going to be 248 times 1, and find the remainder. We get a remainder of 166. Okay, and now these become our new numbers. We're going to continue with that. All right, so we're going to have 248 divided by 116. And it goes in 166, it goes in once. So 166 times 1, and then find the remainder. We get 82. We keep going with 166 and 82. So 166 divided by 82 goes twice, with the remainder of 166 minus 82 times 2, with a remainder of 2. So we're going to say 82 divided by 2 is 41 times 2, with the remainder of 0. Okay, so you want to continue this process until you get a 0 remainder, and then the GCD is the last non-zero remainder in your sequence. So the GCD of the original two numbers, 662 and 414, is equal to 2. And so this is called the Euclidean algorithm for finding greatest common divisors. Okay, let's use the Euclidean algorithm here. So let's take A is our bigger number, B is our smaller one. So we're going to divide So 323 divided by 124 goes in twice. So 124 times 2, and then find the remainder. 323 minus 124 times 2 gives me a remainder of 75. Okay, now this is my A and B. So 124 is 75 times 1 plus a remainder of 49. And that's my A and my B. 75 is 49 times 1 plus a remainder of 26. Right? So 49 is 26 times 1 plus a remainder of 23. 26 is 23 times 1 plus a remainder of 3. 23 equals 3 times 7 plus a remainder of 2. Right, so 3 equals 2 times 1 plus a remainder of 1. Okay, and finally 2 equals 2 times 1 or 1 times 2 plus a remainder of 0. Okay, so I want to carry this process all the way down to a remainder of 0 always, and then the last non-zero remainder is your GCD. So the GCD of 323 and 124 equals to 1. So this means these two integers are relatively prime. Okay. I'm not going to introduce what are called Bezout coefficients. Okay, Bezou's theorem, which says if A and B are positive integers, then there exist integers S and T, such that the greatest common divisor of the two integers A and B can be written as SA plus TB. So basically, I want to write the greatest common divisor of A and B as a linear combination of the two integers. And the purpose for this, the reason for this, will come apparent in the next section, where we're going to do some work with the Bezout coefficients. So this equation is called the Bezout identity, and the integers S and T are called the Bezout coefficients of A and B. So in the next section, we're going to solve like systems of congruencies, which are systems of equations in this sort of mod arithmetic. And this is what the Bezout coefficients are going to be useful for. Okay, so in example 15, we're going to express the GCD of 252 and 198, which we're given that it's 18, is a linear combination of these two original integers. So we basically want to figure out what S and T are. How can I break up that 18 as a number times 252 plus another number times 198? Okay, so we're going to do the Euclidean algorithm to start with. So even though we know what the GCD is, we need the steps for the Euclidean algorithm, because to find the Bezout coefficients, we're going to basically reverse the steps. Okay, so let's take 252 as our larger number. Is going to be 198 times 1 plus a remainder of 54. And then 198 divided by 54 goes in 3 times. So 54 times 3 with the remainder of 36. 54 equals 36 times 1 with the remainder of 18. And 36 equals 18 times 2 with a remainder of 0. Okay, so my last non-zero remainder was 18. So that kind of verifies that I have the correct GCD. All right. So now to find the Bezout coefficients. I'm going to work these steps backwards to solve for the GCD. So we're going to start with this equation right here and solve for 18. Okay, so 18 is going to equal to 54 minus 36 times 1, right? And then we're going to go to this equation right here and solve for 36 and plug it into here, right? So we have 18 is 54 minus 36 is 198 minus 54 times 3 times 1, this one right here. Okay, so now we're going to basically, don't multiply things because it's going to get confusing. We're going to like distribute to get rid of the parentheses and collect like terms. Okay, so I see that I have a 54 and then minus 198 and then plus 54 times 3. Okay, so these are like terms. I have 54 times 1 and 54 times 3. So I have then 198 plus 54 times 4. Okay, so please don't multiply things because we're going to basically get rid of the pattern. We want to kind of collect like terms of the same integers. All right, so now we're going to go to this equation right here and solve for 54 and plug it into there. So we're going to get 18 is negative 198 plus 252 minus 198 times 1 times the 4 on the outside. We're going to distribute to get rid of the parentheses. So negative 198 plus 252 times 4 minus 198 times 4. Okay. So these are like terms. This is like 198 times 1, 198 times 4. So this gives me 252 times 4 minus 198 times 5. Or I'll write it as 4 times 252 minus 5 times 198. Okay, so that's the end of it. Once you kind of use that last line in the Euclidean algorithm, we can basically see that we got this format right here. Okay, so let me just pick a different color. All right, so A and B were my original numbers. So this is A and this is B. This is my GCD right here. 18 is the GCD, right? And the S and the T, the numbers that we're looking for are these numbers, the 4 and the negative 5. Okay, so the 4 that appears in front of the A and the negative 5 that appears in front of the B are the Bezout coefficients. So the Bezout coefficients are S is 4 and T is negative 5. Okay, so this allows us to write the GCD as a linear combination of the original two numbers, which means a integer times A plus another integers times B. Okay, and again, this we'll use, it will be helpful in solving systems of congruencies in the next section. Okay.